It's a real pleasure, Fred, really. I consider you one of the best, if not the best, in our field, and not only a great scholar and inspiration to me personally in my career since we met 1994, Fred, 1993.
I think it must have been the fall of 1992.
Oh,
I
even
was,
okay.
yeah, I was on sabbatical 92, 93.
Great. That was like a year after I have been to UC Davis, and I was so lucky that Fred came to spend sabbatical at UC Davis, and it developed that we worked together. We took a class, and then it also developed to a lifelong friendship and trust between both of us. And of course, every single one of my students online now know you, and I bet of Naveen and all the others also. I diverted very quickly from travel behavior to safety. And maybe I was ahead of you on this front, Fred, to move from behavior to safety. But you did the same, which means, we are thinking together or similar. But anyway, I just wanted to welcome you to UCF. I know you came in person. It was a couple of times, right? You came to our once before we started this Future City work, and then later, I think after we started, and always inspirational. I wanna stress, my friendship and appreciation to Fred. Always, when I seek his help, he's there to support me, and I really appreciate that Fred. You are a true friend, and you are a great person. In addition to being a great scholar, we look up to you all the time.
Thank you.
And then you sent us a gift, which is Natalia, last year. And I remember when I was debating with you, I need to hire someone, and I know how you. So let me think, and then you came up with this. I think before you even told her, and then the rest is history. But we have a friend, kind of a friend in our team also working with us. So anyway, so Natalia, it's your floor now.
Thank you, Dr. Aty. Dr. Mannering's work needs no introduction. However, because I was his PhD student, I got to know some of his other sides that I will tell you about. He's a man of very few words, but his example speaks louder than any words could ever do. As a teacher, he brings lighthearted humor to his classes, as well as car racing computer games to teach his students about safety. He's also known for telling his students that an assignment taking 20 hours would take them 5 minutes, just not to discourage them from trying. His former PhD students refer to themselves as Fred Mannering's academic family and academic siblings. One could even argue that this legacy that will last generations could be sometimes more valuable than any highly cited paper. From my personal experience, I started my PhD when my younger daughter was 9 weeks old. I was powered by a lack of sleep, caffeine, and deadlines. But because Dr. Mannering can always see beyond what's obvious and conventional, and focus on a global maximum solution, I'm having the honor of introducing him today, nearly a decade later. So without further ado, welcome to UCF, Fred, and the floor is yours.
Great, great. Well, thank you both for the great introductions. Well, now I'm sort of embarrassed, but so, wow. With that said, let's get into today's presentation. Now, I should mention, I mentioned to those that were online early, there's a YouTube video of this talk that I uploaded a couple weeks ago, but I think it has like 800 downloads, but it's based on a version of this talk that I gave in Saudi Arabia. So again, just to go over the background, and I talked about this previously a few minutes ago to some people, is I first gave this talk at Penn State in September. Then I gave it at Purdue later in September, then University of Washington in October, University of Alabama later in October, and then Saudi Arabia in early December. So it is, as I've given it multiple times, I've altered the slides, it's gotten better and better. So you're getting a pretty refined version of it, although I haven't given it at USF yet. So maybe at USF, I'll change a few slides and it'll be even better. So I'm going to talk about data analytics and the promise of artificial intelligence to improve highway safety. But it's sort of, as you'll see as I start going through the slides, it sort of looks at how we can use what we've learned from statistics and econometrics to make our use of our artificial intelligence and machine learning better. So let me go ahead to the next slide here. And it looks like it might be, there we go. So let me give you a preview of the conclusions. What I'm going to conclude after I give these multiple slides is that when we apply artificial intelligence and specifically machine learning to analyze data, we have to give consideration to the previous findings in behavioral and cognitive sciences. So there's ideas like endogenous variables, self-selectivity. Those things, unfortunately, we're largely ignoring when machine learning models are being applied to analyze data. So as I'm going to show and give some examples, there's a lot of potential to improve the way we're using AI/ML by giving consideration to what people have discovered in the past studying behavioral data. Now, the problem really becomes important when you're dealing with the human element. If you're not dealing with the human element and you're just into Newtonian physics, then recklessly applying ML to uncover correlations in the data is fine. But when you start getting human elements in, you have to give it a little more thought. So the second point is that AI/ML opens the door for us not just to solve problems previously studied. So as you think of it now, we have these new methods and we're saying, oh, I can apply it to this data. But really what we should be thinking about is applying to these methods to problems that we've overlooked. And I'll talk about some of those. And then also problems that we have not yet imagined. So let's look at sort of the basic definition of artificial intelligence. Is it aims to mimic the problem-solving and decision-making capabilities of the human mind. Now we have to think about how people process information. If you think about the weaknesses in the human problem-solving and decision-making, this is potentially a problematic goal. So we don't want to train AI to think exactly like humans. We want to train it to think better than humans. So when we look at the AI levels, there are 5 levels that I present. And I should mention there are levels beyond theory of the mind where AI becomes aware of its existence and so on. But we're going to, chop it off at theory of the mind. And to start with, you have scripted intelligence, which is like a calculator. Reactive AI is like a Roomba driving around, vacuuming your house. Limited memory AI is a lot of the stuff that we would have in autonomous vehicles. And then there's context-aware AI and theory of the mind. You'll see these upper 2 levels offer a lot of potential for us to combine or use AI/ML and combine it with knowledge that we learn, that we have learned from statistics and econometrics. So let's look at AI safety applications and what things that we should really consider as we're looking through these data. So the first thing we have to look at when we're applying AI/ML is the data size and complexity, the richness of the data. So we have to consider the possibility of a data desert. And this was a term, I think, that was pioneered by Dan McFadden. He mentioned that with big data, we have a lot of data, but there's not a lot of richness. When we're looking at applying when we look at an analysis of crash data, it's actually very rich data because we have a lot of details on the crash. But when you're looking at data that you might get from a bunch of sensors, there's a lot of data that's not necessarily so rich. So the idea of the desert is there's a lot of data, right? There's a lot of ground, but there's only oases of data that are really highly relevant to what you're analyzing. We also have to consider the unpredictable nature of human behavior, the human-machine interface, underlying causality, and I'm going to give a couple examples of that, and then also temporally shifting behavior. So let's look at artificial intelligence applications. I've sort of looked at it in three levels. There's applications of AI that are obvious applications, applications that merit some caution, and then applications that merit extreme caution. So let's look at the obvious applications. The obvious applications would be like video analytics, where you're using artificial intelligence to recognize moving objects. So this would be to determine vehicle pedestrian trajectories, traffic volumes, vehicle information. This is an obvious application. There's no problems with the human interface and so on. There's the interpretation of sensor data, vehicle and infrastructure, connected and autonomous vehicles, really any problem that involves Newtonian physics. And then real-time data processing, because you're not so interested in the causality and all of these higher level concepts if you're looking for immediate short-term predictions. So let's look at applications meriting caution. Here we have, when you have naturalistic driving behavior, so when you're starting to get the human element involved, driving simulation data of large size, but involving human decision makings, when you're predicting trajectories as opposed to just observing trajectories. And really anything with human input has to be looked at with some caution. Now there's the applications that merit extreme caution. And these would be when you're applying like machine learning to small data. Usually statistical and econometric methods are very efficient in determining, and uncovering causality in small data. But so small data applications are sort of you have to be really cautious with. Data analysis that seeks to understand human behavior. This becomes this is a challenge for machine learning, the interpretability of machine learning and so on. Data that's inflicted by unobserved heterogeneity. So even though we have a lot of data, we still have missing, there's still always going to be missing components. So unobserved heterogeneity has to be considered. And then data involving temporally shifting decision-making. So I'm going to give some examples about that coming up. When we look at the data analysis methods that have been applied in safety, we have causal inference models. And causal inference models are applied quite a bit in econometrics. But the easiest way, what the econometricians do with causal inference models is they focus on a specific element of causality, and then they simplify the rest of the data. So causal inference models are not used much in safety because they can't provide the level of prediction detail that we need to make a decision on something like, if I increase the shoulder width from 6 to 8 feet, what's going to happen? Causal inference models simplify the data to uncover causality, but they can't provide predictions on a broad range of elements that we would look for. Then there's traditional statistical models. These are things that you would find in the highway safety manual, negative binomial models, just traditional models. Then there's the heterogeneity models, which are extension of traditional models that add mixing distributions like you would get in a mixed logit model. It looks like I have these automatic slides going. So if I go, I'll have to go back and test that the next time I run through. But as it is now, if it automatically forwards a slide, I'll go back. So the heterogeneity models would include like a mixed logit model and also finite element, finite mixture models, which are, also called, the latent class model. So all of these models that deal with unobserved heterogeneity, and these are extensions of statistical models that account for the unobserved heterogeneity, usually by assuming some distribution of the unobserved heterogeneity, although the latent class models don't necessarily do that. Then there's the data-driven methods, which are mostly in applications of safety, are going to be the machine learning models. And when we look at what has been applied in the safety field, data-driven methods that have been applied in safety include support vector machines, random forest models, extreme gradient boosting, artificial neural networks, deep neural networks, recurrent neural networks, convolutional neural networks, agent-based machine learning, and so on. So a lot of methods have been applied, machine learning methods have been applied to uncover, usually for prediction in safety data. So let's look at, when you decide to choose one of these methods with the data that you have, what are the trade-offs between data size and prediction and causality? So let's look at these trade-offs. Now I have this diagram from a paper that actually Mohamed and I were co-authors on this paper a couple of years back. But this looks at the trade-offs between prediction, causality, and data size. So if we look at a traditional data-driven method, which would be a machine learning method, it's in this red triangle. So that if you're looking at machine learning, you have very high predictive capability. You have excellent big data suitability, but you really don't understand what is happening, right? Even with interpretable machine learning, there's still a problem in uncovering causality. So the causal inference capability of machine learning model is quite limited. If we look at the gray triangle in the middle there that has the traditional statistical methods, there's a big drop in predictive capability. It cannot handle large amounts of big data, but it potentially uncover a little more causality. When we look at the yellow triangle with the heterogeneity models, it sort of expands the traditional models, because using the mixing distributions or latent class allows us to get better predictive capability. Since we're using simulated maximum likelihood, we could have a little bit better, bigger data suitability, and we could potentially uncover causality. Now, I also have the little sort of orangish, light orangish triangle, which is the causal inference models. Again, these are used by economists. They greatly simplify the data and end up with like a regression model where they can use fixed effects and all of these things to uncover a specific causality. So they have low predictive capability because they can't provide the broad range of predictions that we would need in safety. They do not have good big data suitability, because basically you're using variations of least squares regression, but they can potentially uncover causality very well for a specific element. So when we look at data-driven methods plus the heterogeneity models, if you look at some sort of combination of these two, you could see these two cover quite a bit of area in the triangle. And if you did combine the both, you could end up covering quite a bit of area. Now, there are some people that are starting to mix, sort of using information that we learned from heterogeneity models and use them in the machine learning algorithms. But it's still sort of a very primitive early stages of doing that. But there's a lot of potential there. So let's talk about some key analytic considerations and how these various methods would handle this. So I'm going to talk about some behavioral concepts that you can think about while you're analyzing safety data. First is the unobserved heterogeneity. Next is compensating variation, which I haven't talked about, but I'll give an example of how that will work out. Then there's selectivity, endogeneity, and identification, and I'll provide some examples of this. And then there's temporally shifting behavior. So let's talk about these concepts and then think about how these concepts have started to be have been addressed in a lot of statistical and econometric models, but they haven't quite been addressed in the machine learning application. So let's look first at unobserved heterogeneity. So unobserved heterogeneity, as I mentioned before, is data collected for that data that you collect for analysis can never be complete. Even with massive amounts of data from sensors. There's always something that's missing. So statistical analysis methods have developed methods to handle this, such as random parameters models, latent class models, things that I've talked about. But often this unobserved heterogeneity is overlooked in AI ML applications. So what happens when you overlook unobserved heterogeneity is you can get inaccurate predictions and potentially erroneous inferences and conclusions. And there, if you look at the literature, there's a lot of applications of random parameters models and so on that have been able to provide additional, significant additional insight. So let's look at the second element, which is compensating behavior. Here, the introduction of safety innovation changes behavior in somewhat unexpected ways. So I'll give an example. There's a technological innovation that improves safety. What will happen? So here's an example, and actually this is a paper that I wrote, I think back in 2006. It's a variation of that. Let's look at what happens with compensating behavior. Let's say we have a safety feature that we're introducing, and we have some initial conditions. And in the initial conditions, we have a curve that gives the trade-off between selected normal driving speed and the probability of a crash. So if you start driving faster, your probability of a crash increases. So in initial conditions, each person will have some equilibrium. It's like, well, I like to have a 1 in 10,000 chance of being killed in a crash, so I'm going to drive at point A. So what happens when I put in a safety feature? This could be a safety feature in the car, some improved braking or lane departure warning, thing like that, or something you physically do to the road. So if there's a safety feature that's introduced, it will move this curve down. And here, the safety innovation, the assumption that we almost always make when we're doing safety research is that the effect of the innovation will all be extracted in improved safety, which means that we will keep driving at the same speed and we'll move from point A to point B. So the safety innovation, everything is being taken out and improved safety. But realistically, what happens is that people will start compensating. It's like, you are making this road safer for me, but I still I have a 1 in 10,000 chance of having a crash. And if there's complete compensation, these people will move from point A to point C. And at point C, they'll keep their 1 in 10,000 chance. Now, realistically, what happens? There's probably going to be some compensating behavior going on. This happens a lot when we put in a safety innovation. We have expectations that it will improve the safety, and we're always disappointed when it doesn't quite improve it as much as we had hoped. And compensating behavior is one reason why that may not be the case. So realistically, most people will not move totally to point B, but they may have somewhere between point B and C. Maybe it's something like point D. There's also a possibility they grossly overestimate the effectiveness and they move to point E, and that's actually, they end up less safe than before you had the safety innovation. So if you ignore this compensating behavior, it leads to an overestimation of the safety innovation effectiveness. And it also, you will find unexpected consequences. But really, you should have expected these consequences if you had thought about the potential of compensating behavior. So let's look at selectivity, endogeneity, and identification. And this is one area that we have conveniently overlooked, I think, in a lot of safety work that we've done. So safety data is often afflicted with a selection process. And we have two examples. For crash data, the crash data that we collect from police reports are going to have risky drivers overrepresented. This is particularly problematic during the COVID, because during the COVID lockdowns, the types of drivers on the road changed dramatically. And so, but this is something that some papers have talked about this, but correcting for it in the nonlinear models that we use in safety is very difficult. The other way to think of it is that drivers observed on routes may be a self-selected group of safe or risky drivers. So for example, and to give you an example of what could happen here with this selectivity, suppose you had a very dangerous intersection, and the intersection is dangerous so that the safest drivers avoid that intersection. So then you make an intersection improvement, and now the safe drivers start going to that intersection, but the intersection becomes congested, and the risky drivers that used to go to that intersection start going to other intersections. So what you find out is that your improvement on one intersection causes increases crashes elsewhere in the network. So that could be explained by the selectivity process. So for selectivity, endogeneity, and identification, the consequences of self-select data is that you will have biased safety predictions, and it looks like I got my Odyssey, biased safety predictions, and you're unable to identify causality. So let's take a look at a couple examples of identification and self-selectivity. So let's look at the identification example, and a good example is like motorcycle safety. So suppose you have a model, you estimate a model, and you have an indicator variable that's 1 if it's raining and 0 otherwise, and you find that rain increases injury severity. But so that's great from a statistical point. If you did machine learning, it would show, yeah, there's a great correlation, blah, blah, blah. But what's going on here? There's 2 possible explanations. One is that rain does increase the injury severity for reasons you would expect, like, there's reduced friction, there's going to be a higher probability of a crash because of reduced friction and reduced visibility, all things associated with rain. But the second explanation would be that only the riskiest riders choose to ride in the rain, and they would have more severe crashes, whether it was raining or not. So the effect of the rain variable, you could argue, although it's probably unrealistic, could be a pure selectivity, and the rain has no effect. It's just that the rain causes the riskiest drivers to make up a significantly greater portion of the people driving during the rain, and they have more severe crashes. So realistically, it's probably a combination of these 2 things, right? It's probably some Newtonian physics involved, but there's also some selectivity involved, but we don't know what's going on there. So it gets to give you another selectivity example. Let's look at the effectiveness of vehicle safety features. And this is actually a study I did in I think it was like 2004, 2005. We look at the case of side impact airbags, and side impact airbags are found to reduce fatalities relative to vehicles without side impact airbags. So I remember when side impact airbags were first introduced, the National Highway Traffic Safety Administration said that in side impact crashes, they were like 40% effective based on the data that they collected in reducing fatalities in side impact crashes. So the question, though, is that when a new safety feature is introduced in a vehicle, the people that are most likely to buy that safety feature first are the safest drivers. And so this is this is a selectivity example, because the safest drivers buy the safest vehicles, and the safest drivers tend to have less severe crashes. So if you look at historically what goes on with the estimated effectiveness of side impact airbags, you find when when they were first introduced, they were like assumed to be 40%, then it came 38, 35, 28. The reason why it kept going down is that eventually the risky drivers start driving the side impact airbag cars, and then you truly find out what the effectiveness. So you cannot just look at people with the cars and the people without, cars with the side impact airbags and cars without, because the people that are buying these cars are fundamentally different with fundamentally different risk levels. So, and again, so one reason the self-selectivity, again, as I mentioned, the safest drivers buy the new safety features first. Now, there are statistical corrections for this. Let me get to the next slide. And James Heckman at the University of Chicago actually shared the Nobel Prize with Dan McFadden in 2000 for his work on this, in developing a selectivity correction term, But unfortunately, the selectivity correction term that he developed is for a linear regression model, and sort of applying a Heckman-esque approach to the complex models that we use, like Mixolydian and stuff, is a mathematical nightmare. So we cannot develop a statistical correction that's as clean as the Heckman approach. But this whole sort of notion of self-selectivity, we think about this when we're doing econometric models, although we probably don't address it as much as we should. But this is a problem that's been largely ignored in the application of artificial intelligence and machine learning. So let's look at these, sort of the last point in these four is the temporally shifting behavior. Now, if we think from a cognitive science perspective, human behavior is continually evolving. And as you introduce safety features in cars or redesign roads, people are constantly changing how they adapt to these safety and their safety features. And there's larger things going on with economic conditions, distracted driving, changes in the use of electronic devices. There are many, many things that are going on. So if you look at the cognitive science literature, there's many reasons to suspect that human behavior is changing temporally over time. So these behavioral shifts can be induced by technological innovations, natural changes in risk perceptions, changes in societal norms, lots of things of this nature. So, and there's ample evidence in the safety and travel behavior literature that shows that model parameters change significantly over time. And if you look at the literature, there's tens of, maybe even hundreds of papers that show that if you estimate a model with 1 year and you estimate it with another year, there's a statistically significant difference in the parameters from 1 year to the next. But uncovering what causes people to change, and more importantly, how those betas that you estimate change over time, this is something that the econometrics field is still dealing with, but presumably the application of AI ML could also provide some insights into this. But basically, if you ignore temporal shifts in the parameters, your parameters are simply incorrectly estimated, and you'll get erroneous inferences and predictions. So let's, what do these sort of elements mean for AI ML safety applications? It means, we have to think about things like unobserved heterogeneity, selectivity, identification. Just think about these things and how we might be able to incorporate them into sort of machine learning algorithms. So if we do not recognize the safety complexity, these 4 points that I brought up, with and underlying causal effects, we're going to, this is highly problematic. And it's particularly, it's particularly problematic when we have non-real-time data. In a lot of real-time applications, the selectivity of, you're processing the data immediately and making really short-term predictions. You don't have to be as concerned about the temporally shifting parameters and all of these longer-term effects. But when we think about it, we have to think about causality and not just correlation. And when you think of machine learning algorithms, they're not set up to uncover causality. Even interpretable machine learning is not, uncovering causality. The example I give is, all of the statistical models are interpretable, but a lot of them have so many flaws with, biased parameters and so on that they're really not. Just because it's interpretable doesn't mean that's uncovering causality. So let's look at the promise of artificial intelligence, machine learning. And the example I'll give is the example of adverse weather, what a human response would be and what an autonomous vehicle response might be. So let's look at the human reaction. So this goes back as a slight variation of the graph I gave earlier with risk compensation. So with human reaction, you're going to have uncertainty about the probability curves with the trade-off between selected normal driving speed on the horizontal axis and the probability to crash on the vertical axis. And there will be a decision that humans make whether or not they want to retain the same level of safety. So in this case, we have some normal weather conditions where the humans start off at an equilibrium point at point A with like a 1 in 10,000 chance of having a crash. It starts snowing, of course, not in Florida. It starts, maybe raining in Florida, or, maybe you get some ice or whatever. So that shifts this curve up. And if you keep driving at the same speed, you will move to point B, and you'll have a much higher probability of a crash. If you perfectly analyze what's happening on the road and you want to keep your 1 in 10,000 chance of having a crash, you'll move to point C. But realistically, you'll probably be somewhere between B and C. I mean, it's possible it starts snowing, you become super conservative, you go down to E, but it's unlikely it starts snowing, you'll say, hey, it's snowing, let's see if I can drive faster. It's unlikely to go above point B. But for an autonomous vehicle, this you could be much better. For an autonomous vehicle, we would have the curves, first of all, would be at a much lower level because the probability curves will be lower because we do not have human reaction time and we can have these immediate responses. And there'll also be near certainty about the probability curves because we'll have all these sensor data. We'll be able to immediately do all the calculations for the probability, stopping distances, and so on. And we can also, the autonomous vehicle can correctly, I mean, you'll never have a 0% probability of a crash, but it can correctly keep, I'm not sure if it'll be a 1 in a million probability of a crash, but there will be no compensating behavior because the autonomous vehicle can be programmed to go from point A to point C. But this gets in mind, we can think of how we could have what I call AI-assisted driving. So you could develop again, a human-driven vehicle, but it had safety features that interact with the human. So the idea here is that it's still being a human-driven vehicle, but it's advanced. You're getting all the safety information from the sensors in the vehicle. It could correctly calculate the speed crash probability curves, but it could appropriately adjust the vehicle systems after learning driver responses to changing conditions. So the idea here is that it can have a memory of how you're braking and so on, and it would be able to detect if you're starting to engage in risk compensating behavior. So it could make the car seem more dangerous than it actually is, so that you don't start driving faster when you have better brakes, for example. So what could happen, again, let me see. What could happen is it could mitigate, you could design an AI system in a car, in a human-driven car, that could mitigate the risk compensating behaviors and potentially other safety mitigating human behaviors. So the idea of having like an AI-assisted driving, still in a human-driven car, it would correctly calculate the probability curve. It can adjust the vehicle systems after learning driver behavior responses to changing driver conditions, and it can mitigate risk compensating behavior. So what role will AI ML play in improving safety? And let's take a look at this. So currently, AI ML applications in safety are often being applied without much thought to sort of the basic understanding of safety. All of the things that statisticians and econometricians have been thinking about, even cognitive sciences, all of the behavioral elements. So when we think of it now, artificial intelligence is an ML. It's given us an incredible tool, but we're using it like a hammer instead of a nail. Instead of thinking about what we should have learned from econometrics and cognitive sciences, all of the stuff that we've learned about self-selectivity and things, we're not bringing that currently not bringing that to the table. So the other point is that when, we often justify machine learning, is that we compare it to an econometric model and says, oh, look, our machine learning model predicts better. That's a very low bar. If you go triangle that I had before, if you cannot develop a machine learning program that outpredicts an econometric model, there's something seriously wrong with your machine learning. because all you're doing is digging around for correlations. You're not thinking about causality, endogeneity, identification. And if you just had a econometric student who never had econometrics, what they would do is they'd throw every variable in the model and it would actually predict better, right? But you wouldn't know what was going on. You would have a lot of statistically insignificant variables and so on. So that's not the measure that we should be using. And what makes statistics and econometrics still important is it uncovers causality. We're not doing that in ML, but we have to start thinking about how machine learning can help us uncover causality and all these concepts that we've been thinking about for decades in econometrics and statistics. So when we look at AI/ML for safety analytics, we should think, again, as we're doing it now, mostly we're thinking of AI/ML as a new way to solve old problems. But what we should be doing is thinking about it as a tool to explore problems that we've conveniently overlooked, like the compensating behavior we've overlooked a lot, the self-selectivity in crash data. We haven't really looked at that in great detail. Or, and this is important, we can use AI/ML to study issues that we've not yet imagined. And I'll give a couple examples here. Let me see. So for the conveniently overlooked, selectivity in the data, temporally shifting behavior, we have papers that look at temporally shifting behavior, but we don't know how the betas are shifting over time. We look at it, it's like, well, look, there's a difference between betas in 2 years, but we don't understand how the betas are progressing through time. And we usually overlook compensating behavior. Then there's the things that we've not yet imagined. So thinking of these, we're going to have a long period where human-driven vehicles are in the vehicle fleet with autonomous vehicles. And we can think of putting, as it is now, we're just throwing autonomous vehicles into the vehicle fleet and training them to avoid, human vehicles. But an alternative is you can put autonomous vehicles into the vehicle fleet and have the autonomous vehicles train humans. So let's look at how this might. So autonomous vehicles could mitigate dangerous human behavior by managing the machine-human interface. And we can use autonomous vehicles to alter the behavior of human-driven vehicles around them. So let me give you an example of this. So when we think about current autonomous vehicle thinking, the current approach is that we design autonomous vehicles to avoid collisions in response to human-driven vehicle trajectories. Now, we also design autonomous vehicles to avoid collisions with fixed objects and stuff, but relative to the human autonomous vehicle interaction, that stuff is trivial. But we're still going to have a big problem when we start getting higher and higher percentages of autonomous vehicles in the vehicle fleet. So the alternative approach here would be to design autonomous vehicles to interact with human vehicles to alter the crash critical vehicle trajectories before they happen. So the idea here is that the autonomous vehicle could detect a human vehicle driving too closely to it and could flash the brake lights or do changes in acceleration and deceleration to change the behavior of the human-driven vehicle. Now, if we look at the problems that we're going to have, the likely consequences of ignoring the human response to autonomous vehicles, we are going to find, and people have already have anecdotal stories about that, is human driving behavior will change in fundamental ways around the predictable driving of autonomous vehicles. So if you identify an autonomous vehicle in front of you, you can tailgate it, you can cut it off because it's going to have very predictable behavior. Now, unfortunately, the behavior that you start developing around an autonomous vehicle is going to be propagated into the behavior with human-to-human vehicle interactions. So if we keep throwing autonomous vehicles into the human-driven vehicle fleet, as we're now doing, almost certainly we're going to have an increase in human-to-human crashes, because people are going to start driving around autonomous vehicles much differently, and there's going to be such a huge disparity between autonomous vehicle behavior and human behavior that we're going to generate very risky behavior. And so the second thing I have here is, changes in behavior around autonomous vehicles will potentially create, not potentially, will certainly create unsafe behaviors around human-driven vehicles and increase human-to-human crash rates. And we're going to start noticing this, especially when we start getting autonomous vehicles, even like 1%, 2%, 3% of the population. We're going to start noticing increases in human-to-human crashes. So what's the future of AI, ML, and safety? I think it's important to integrate data-driven analytics, which are all of the machine learning approaches in AI, with the causal principles of econometrics and cognitive science. So as we start applying AI and ML more and more, we have to start thinking about what we've learned from traditional statistics and econometrics. So we also have to draw from the fundamentals of cognitive science to interact AI ML with human behavior. Because if we had all autonomous vehicles, this would be a very trivial problem, right? But we're going to have decades where we have autonomous vehicles interacting with human vehicles, and we have to make sure that our AI can interact with human behavior and adjust accordingly. So now there's several papers that I've written over the years with colleagues that have discussed these concepts. Again, there's a YouTube video that has all of this, so you can pause it if you wanted to look up any of these. The oldest paper I have is the paper that looked at the risk compensating behavior. That was from 2006 with the side impact airbags. So if we look at sort of the overall effect of here is that AI ML gives incredible opportunities for us to analyze data in exciting new ways. But we really have to think about not just applying these methods to old problems. We have to think about what the potential is for it, for it to significantly improve safety. And this idea of having autonomous vehicles interact with human-driven vehicles. So you don't want the autonomous vehicles to learn from the human visit. And it looks like my program. There we go. We don't want we don't want autonomous vehicles to learn from human-driven vehicles, because that could be a disaster. If you had an autonomous vehicle that was trained in Boston and then you brought it to like the Midwest, it would be a mess, right? We want to develop autonomous vehicles that actually make the human vehicle drivers around them better drivers. So I think that's, and I have to, when I go back and do this, I have to stop that auto forward that apparently I have going on here. And I think I might be able to, quit sharing my screen and also turn on my Zoom camera. Let's see if that's going to work. Ah, yes.
Thank you, Dr. Mannering. Very thought-provoking presentation, and very exciting, and the way you summarize, decades of research in safety, and especially, the comment on AI and ML, without thinking too much, I think was very interesting. I think very useful for our students. Now we will open the floor for any questions.
And I should mention, if you Google my name, my Google Sites, you can link to this AI ML video, and then you can fast forward, go to the points that because you can see if I missed anything in this live talk. When I was said that, well, I could just play the YouTube video and then answer questions at the end, but the YouTube video is very good, and it has the same background. Although I think I had different guitars during the YouTube video. I should tell you, I have like 22 guitars, and I have 5 that are out at any one time, and I change them from time to time. So if you look at changes in my background, you can see slight variation.
Okay, perfect. Good to know. So we have first hand from Dr. Aty. Please go ahead.
Yes, sir. As usual, very inspiring, and I agree maybe 99% of the time with your thoughts. So, and I want to reflect a little bit back about the safety data. So most of the econometric and statistical data was developed in econometrics, and then when we got it in transportation, it was mostly the travel behavior research, and and adapted, and etc. And the travel behavior research tend to be richer, but more difficult to predict. You have these surveys, you have these daily diaries, and you collect really extensive data about the people traveling and the reasons and all this. So behavior becomes the center. In safety, if we go back, it is mostly the crash data. And I agree with you, the crash data is self-selective. It has selectivity bias, of course, over-representation of certain groups of the population or certain conditions, etc. So I totally agree with you. And then, luckily, recently we started to move away, not entirely. Still, the crash data is the prime source of data that we use most of the time. But we started, as you said, looking at the more real-time data, the more kind of microscopic data, etc. So this is kind of a history of the safety data. So if we talk about the crash data, which I think the majority of the work is still in the crash data, the problem, it doesn't have any behavior. It doesn't have any indicators. I understand that you can, statistically correct some of the biases or some of the issues, but the essence is that it does not have human data. The maximum you get, and we claim that we use the human as the age and the gender. Except we are accounting now for the assuming that all males behave the same way or all females behave the same way, which is
right,
right. So I think it is that. The other thing I wanted to mention to you, and I'm not sure what you're feeling about it, is a lot of the work that we did, we started to look at the case control type design of safety data, which is look at the crash situation at the same location versus non-crash situation. Okay, but these types of models do not look at the frequency type models, which is the number of crashes at a certain location. It looks like a crash by crash as an event, and compare the characteristics or the conditions but again, it doesn't include behavior.
Yeah.
So for example, if we look at ADAS, of course, I'm very intrigued by what you said about affecting the human drivers to behave in a way. I think that's fascinating, really. If we find a way to implement it, it's really fascinating. And I would think you need to talk to car companies that are very rapidly developing these ADS and automated driving, to consider this, because yes, they use trajectories in their algorithms. But for example, if we consider the case control, and this is what we have been doing, like a vehicle with the ADAS systems versus a vehicle without ADAS systems, and a crash of this vehicle at a certain location versus a crash of the other vehicle at the same location. Okay, and trying to understand what is the difference when you equip with the technology of it. Okay, now we can also look at an ADAS system at a certain location versus no crash at that location. Because I mean, you know what I'm saying? That so it's like two comparisons. But I'm not sure how to do that, because no crash is no data to start with, right?
Yeah.
Your data is based on a crash. So anyway, so just a little quick thoughts, so that we find out of time. But the data issue and the lack of behavior issue in the crash safety data, and then what you think about this case control type analysis for safety.
Sure. Yeah. So I think with traditional crash data, there's a lot of problems. We don't have the safety. I mean, we could say, well, we can account for all females aren't the same, but then we have to assume a mixing distribution, right? That the effect females are normally the effect of females are normally blah blah blah. But basically, I think we've hit the brick wall with what we can do with statistics and econometrics, we're at the point where we need something, the models are so complex. We can think about what we could do and what we could get if we had safety, if we actually had the sociodemographic information, the detailed risk analysis information you referred to. But really, I think the time is right to start getting AI ML and start introducing that into statistical models. Now, with your observations with the crashes, I mean, there's a lot of work that now look at, near misses, and of course you're familiar with that, post encroachment time, all of that time to collision. So we can potentially get a lot of detailed information on near misses. And, so that we don't necessarily have to wait for crashes, but there's still, when we think of that, even if we're collecting data from video analytics, there's still a selectivity going on, because if we're collecting video data at a specific intersection, if it's a dangerous intersection, certain groups of drivers may be avoiding it. If you change the signal timing, you could get a different group of drivers arriving. And we don't know, you could think of, imagine we could do facial recognition at some point, and then I could link this to all of your social-demographic information in some, incredible database, and then we could get the behavioral information, and we could actually, collect. We could have the cars monitored so they do experiments and get all sorts of risk analyzing data. I mean, it's incredible what we could potentially do, but there is also the problem that we have companies developing AI ML as proprietary information, so there's sharing of data problem. There's a lot of obstacles that we'll have to face. And the other thing that we have to be careful with is when we do sort of, even like in a before and after study, the fact that people's betas are changing over time, it makes it very difficult to do a before and after. If you go more than 6 months, how much of your safety improvement is just like natural changes? It's very difficult to control for all of these things. So maybe, and econometrically, it's a nightmare with the models, the nonlinear statistical models that we use, doing a selectivity correction. If you could pull it off, you would win like 3 Nobel Prizes in economics. I mean, it's almost an impossible mathematical and computational problem. But this, the potential that we, by having sensors and AI and ML interact with this behavioral stuff, as Mohamed, you mentioned, that we've learned from like the behavioral sciences and travel behavior, there's a potential to do more. But it's, I guess the bottom line is we've thought of almost everything that we can do with crash data. And we've looked at trajectory data. It's like, okay, we're not getting enough crashes. Let's look at trajectory. There's so many things we thought of, but we have to start thinking about combining the methods. As it is now, we have an econometrics camp and a machine learning camp. And the machine learners, I should tell you, it's a new field. People have take a machine learning course and they start applying it to everything. They have no idea what's going on, right? And it's the same thing with econometricians. I have students that use mixing distributions. They don't know what the heck's happening. It's like, but so there's time though, if we step back and think about, logically how to apply these, there's a way of combining these that we, so for example, I had, in some of the temporal analysis I've done, I looked at risky drivers versus non-risky drivers. And what I found is that risky drivers, their parameters change much more over time. So this suggests, we're finding temporal shifts in parameters over time, but it's probably a small group of drivers that are motivating the temporal shift. There's probably a group of drivers that really don't change their risk profiles dramatically over time. But there must be, there's probably ways of identifying those. And, perhaps having an intelligent car that, could collect information in real time on their braking and performances and stuff. We could develop risk profiles of individual drivers. I mean, there's a lot of things that we could imagine. But I think to Mohamed's point is well taken. We sort of hit a wall of what we can do with, I mean, we can make incremental improvements, but it's time to step back and think about how we can interact these new methods with the methods that we've studied with for decades.
Thank you, Fred.
Okay,
Thanks.
Thank you, Dr. Aty, for the great question. Now we have 3 more hands, so we'll go in order. Natalia, then Shahbaz, then Jizin. Please go ahead, Natalia.
Thank you. And thank you, Dr. Mannering, for the great lecture. Since we have a lot of students joining us today, I do have a question on their behalf, because you've seen the paradigm in transportation and the methods change over the years, the submissions in your journal, and how the interest has been shifting. And we talk a lot about there's the machine learning camp, and then there's the econometric statistical camp. What advice would you give early and junior PhD students where to focus to be successful for the next generation in transportation?
So I think the focus, I should tell you in my journal, if it's got machine learning, it's almost always rejected, right? But if it has machine learning with econometric models and tries to uncover causality, then so my recommendation, machine learning is the future, right? But I would recommend understand what's going on in econometrics, understand things like endogeneity, causality, self-selectivity. And if you understand those things, then when you start thinking about what you could do, you could, for example, develop a machine learning algorithm that could detect, go through data and identify when there's a potential selectivity bias problem. I should tell you, a lot of people that apply econometrics don't even think about the possibility of selectivity bias, right? And so but then when it's pointed out, the econometric correction may be very difficult. So my recommendation is take some courses in econometrics and behavioral sciences, but then think about how you can use what you've learned in that course to improve machine learning and AI algorithms. Because that, AI ML is going to be the way. Now, I should tell you, my oldest daughter, I think with, several of you met at TRB, she works at the Applied Physics Lab at Johns Hopkins, and she's doing artificial intelligent interface with fighter jet pilots. It's funny, we were talking about equity proposal, and I said, we could get my daughter, and she would look at the equity between targeting poor people and targeting rich people when you're bombing them. So, but there are a lot of things that she's working on, and again, she's a cognitive scientist. So even though she's working at the Applied Physics Lab, they have her there to get the cognitive interaction between AI and the fighter jet pilot. And we're going to have the same sort of problems. We could generate a lot of AI data, but we could actually use that data to interact and make better drivers, right? So that interface between the AI that we're developing and then how the humans respond to that, that's going to be the future. So bottom line is take econometrics, some behavioral analysis courses, and then think about those fundamental concepts there and think how that could improve the machine learning. So just taking a machine learning course and recklessly applying it to data, I mean, you can always publish a paper somewhere. I mean, so you could get a publication, but think about these more fundamental things. And then I think you get a publication you could really be proud of. So I think that's where the future is thinking about what we've learned for decades, but thinking how these new methods could help us do what we've learned better.
Perfect. Thank you, Dr. Mannering. Shahbaz, your question?
Hi, everyone. So, Dr. Mannering, first of all, it was a brilliant presentation, and I think it asks the right question of like how to rightly analyze the crash data and all the things. And one of the major parameter that came up is the behavior. And as Dr. Aty said, that the main problem, like the wall there is this behavior. There is how you get it. It is ever changing, right? So one question I have about that is, with the advent of the large language models, which are a combination of the human behavior from all over the world, because those models are trained on the language that is present on the internet. Like, is there any way you think like to combine the language models and with the advent of the vision combined with the language model? So now the language model can also see, on the images, and as they are improving, they can actually analyze video streams. So since they are a combination of human behavior, from all over the globe, can that be like a solution to this problem, to this human behavior, lack of human behavior data?
Yeah. No, I think the solution, though, would probably be to apply that at a more disaggregate level, where you could collect information on an individual in a car, and then use that AI to process that information very quickly, and you could get the disaggregate effect. You could get an individual's risk profile that would be changing in real time, right? And that could be used, and depending on how you would upload that into a larger database, I think the important element, with regard to your question, is the scale. If you were to get that at a individual car level, that would be incredibly valuable. If you go to a larger scale, it could still be valuable, but perhaps less so than at the individual vehicle level. But as you think about, as these cars continue to develop, it's only a question of time before you can get a sufficiently intelligent AI system in the car to actually start collecting this data. Then we would have the information that Dr. Abdel-Aty was talking about. We would be able to get the detailed information on specific people and start adjusting, vehicle safety features or whatever to significantly improve safety. And this all, you can think about this, all gets into vehicle-to-vehicle communication. I mean, it's unbelievable what we could potentially do. But again, the tools that we're developing are starting to open up these possibilities, but I don't think we've thought about what we could do with that. And this idea that I just threw up of having the autonomous vehicles train drivers around them. You could have an AI-assisted vehicle that would train you to be a better driver without even you knowing it, right? And then it could also transfer the information from your driving behavior to a higher level, where it can be interpreted at a higher level, so you can get the aggregate effect of safety and so on. So I think I think definitely but there is the scale element. It would be nice to get down to the individual driver to be able to get that level of information.
Right. Thank you, Dr. Manning.
Thank you.
Jason, your question, please.
Yeah. Hi, Dr. Manning. Thank you for your very innovative speech. And I cannot agree more with the considering the human effects of when developing autonomous vehicles. So my question is from the perspective of developing autonomous vehicles, developing autonomous driving algorithms. So what could you kindly suggest the directions, methods, or even research tools that can help us to investigate the interaction effects of AV and human-driven vehicles, and then help us to advance in autonomous driving? Like for myself, I work on driving simulators, so I would say a powerful driving simulator that is capable of simulating the interaction between the autonomous vehicles and human drivers. So I would know your thoughts.
Yeah, so that's we should write a proposal together, because that is the frontier, right? If you could start thinking about, and as you mentioned, driving simulating environment is really good for that. Start thinking about how you control the vehicle, then monitor behavior around it. Now, this is an incredibly complex problem, because there's a lot of cognitive science and stuff, but even collecting some initial information could open up a lot of possibilities. Having a vehicle, and then using that vehicle to train the driving behavior, and then do repeated experiments and stuff to see how the human behavior responds to different reactions. I mean, that's sort of step one to actually putting something like that in the field. But that, I think that's just one of the, that one in particular. And you can also think of autonomous vehicles, and some people have done some work on that. They could, they could presumably be used to reduce congestion, right? Because they could be used to control the speed of traffic and interact with this, so there's more macro effects that they could have. So there's a lot of potential there. I think we're at the point where we figured out that technically we can throw an autonomous vehicle into the vehicle fleet and it doesn't run into walls and stuff. We can now start thinking of these higher order ideas. It's like, well, we're not so much interested, okay, it doesn't hit the wall anymore. Let's see how it interacts. We can start thinking of these higher intellectual elements of the problem.
Okay, thank you, Dr. Manning.
Thank you so much.
Last question, I think,
Thanks.
from Ding. Please go ahead.
Hello, Dr. Mannery, and thank you for your wonderful presentation. I have a question similar to Dr. Aty. For example, we conduct a case control study. If we have the data of autonomous vehicles at one location, and you just mentioned we can use the video data to extract the near-miss events. Do you have any opinions about how to link the near-miss events with the crash data?
So yes, I work using some traffic conflict data with my colleagues at Queensland University of Technology. So now here's sort of, we sort of view crashes as the gold standard, right? And I would argue that maybe crashes are not the gold standard. And here's the analogy I use. And some of you may be hockey fans. I know Natalia's a hockey fan. So this is ice hockey. So when you look at ice hockey, if you're a fan, you look at goals scored, right? But if you're actually looking at hockey analytics, they don't look at goals scored, because I remember, and again, I'm a Pittsburgh Penguins fan because I grew up in Pittsburgh. I remember they interviewed the Pittsburgh coach, and they said your power play, and the power play is when the other team is at a one-person disadvantage, sometimes two. But they said your power play has been incredibly ineffective. Are you going to change it? And he says, no, our data analytics show that our power play is above average expected goals. The actual goals scored, which would be the equivalent of a crash, the goals just weren't going in, because sometimes a hockey goal is, the puck is shot, it bounces off somebody's head, bounces off somebody's leg, and goes in the goal. That would be like a near 0% probability, right? So I always argue that, people say, well, what about crashes? Maybe we shouldn't be so focused on crashes. It's the near misses. If you look at people that are doing sports analytics, they're not focused on goals scored. They're focused on, the likelihood of a goal being scored. And that's what they're using to determine their lineups and so on. So this is why if you're submitting a paper to Analytic Methods and Accident Research, we do not use the word surrogate, right? Because surrogate sort of says crashes are the gold standard. We just say it's a traffic conflict. We're not, I'm not willing to concede that crashes is really what we should be looking at. Now, obviously, long term, there's going to be a correlation between crashes and these near misses. Just like in hockey, long term, the effectiveness of your power play is going to be correlated. Number of goals you actually score is going to be correlated very closely to the number of goals you're expected to score from the data analytics. So that, I think, I think a lot of people spend maybe too much time trying to correlate crashes with near misses. You should just look at near misses and say, maybe this is what we should be looking at all along. So that, again, that's just one argument. So I don't think, but when you think about how the safety field developed, and, when Mohamed and I were young researchers, the crash database was the gold standard, right? Because that's, it was a lot of data, you could get it instantly, and everybody realized it's a crash. But you have to realize a certain portion of the crashes are just ridiculously random events. A deer runs across the road or something really weird happens there. It could be normally a very safe highway, but maybe near misses is what we should be looking at. So, to answer your question, I'm not sure it's so important to correlate crashes. And especially if you looked at expected number of crashes and actual crashes over a 10-year period, they should be very closely aligned. But if you look at it over a 1-year period, they might be quite different. And this gets back to my Pittsburgh Penguins power play. This is like 8 games they hadn't scored a goal, but during those 8 games they had above average goals scored. And as it ended up happening, he didn't change his lineup, and eventually they started scoring goals. But if you were focused on goals scored, you would have changed your lineup when really there was nothing wrong with your lineup. And that could be that could happen at some intersections. We put in improvement because we have a lot of crashes, but it really wasn't all that dangerous. It could be just random events. Now, I should tell you though, in the long term, the crashes and the expected number of crashes, they asymptotically converge, but we have to be careful with shorter time periods. So yeah, maybe you shouldn't worry so much about correlating crashes and traffic conflicts.
Perfect. Thank you, Dr. Manning, for the detailed response. So to end, Dr. Manning, I have a comment and a question on the discussion that we were having, that when the autonomous vehicles start coming into the vehicle streams, how the human drivers would react. I always thought that, initially we would bully them, cut across, tailgate and so on. But the safety implications, I never thought through that might change our behavior as human drivers in the long run. So I was just thinking, during your talk, how could we avoid, changing the human behavior? So you propose we could change it positively, but at least keeping it the same level,
Mm-hmm.
So do you think we could introduce some stochasticity in the behavior of autonomous vehicles? Maybe they honk, when
Yes.
or something like that. And maybe, it leads to Tesla versus Waymo, who is more aggressive driver. And maybe as a consumer, I would like to buy that vehicle for my, because if I'm sitting at the back seat, I would not like to be bullied. I would like my vehicle to
Right.
back. So maybe a good research opening there. What are your thoughts on that?
Yeah, no, those are two very good points. I'll give an anecdotal story about how people change their behavior. I have a colleague who has their cousin or something has figured out when he's driving in California, when he's driving behind an autonomous vehicle, it's programmed to pull to the side of the road when the car behind it starts beeping its horn. So he's driving on this road. The autonomous vehicle is going 35 miles an hour, the speed limit. He wants to go 45 or whatever. So he starts beeping his horn. The car pulls over and then he drives right by it. So you can imagine how people are going to quickly adapt. So your point, though, is when we send these autonomous vehicles out into the fleet, it's important to have them behave sort of like a human driven vehicle, where it's flashing its brake lights, it's detecting it's being tailgated. So instead of just going along, it flashes the brake lights, accelerates, decelerates. It programs it to behave more like a human. And then you wouldn't have these potentially adverse consequences. Because if you program it as being very predictable, as I mentioned in my talk, then and especially when you get up to like 20 or 30% autonomous vehicles, then the humans are going to say, oh, almost all the vehicles behave like this, and then you cut in front of somebody that's a human-driven vehicle, and then something completely different happens. So there's a lot, there's a lot of possibilities there.
Which human, from Boston or from the Midwest?
Oh yeah, that's it. Because for example, when I was a student in Boston, it was a common thing. I'm not sure if it's still like that. If the light turned red, people would still go through it for like 3 or 4 seconds because I'm not sure if they knew that all red was 2 seconds or something. It was just a tradition in Boston that when the light turned red, it was understood that you had a couple more seconds to go through. And actually, somebody was made a left turn in front of my wife. And when the officer came to the scene, her excuse was, the person that pulled in front of my wife, was yes, the light was red, but it just turned red. So, and she's arguing with the officer, but it only been red for a couple seconds. No, red means you have to stop. So it's interesting. And and if you start driving in Boston, you start adapting to that. It sort of becomes understood. So you can imagine if you trained autonomous vehicles in one city, or you can imagine in extreme case, you would train an autonomous vehicle in Rome, Italy, and then you put it on the streets in America, you know, it'd be like driving around in circles,
Right.
and then who knows what it would do, right?
Yes, yes.
So that's something that, you know, just think about. You have to be careful training autonomous vehicles don't learn from stuff around them, that they're actually
Yes.
designed.
So the algorithm changed based on the city. I think
Yes,
more
but it
work
would,
for the
yeah,
company.
you could probably get a different starter algorithm. You'd
Yes.
probably, so if you had an autonomous vehicle trained in Boston, you would have to erase the memory and get a starter algorithm for Orlando, right?
Yes. Right, right, right. So
You
since,
probably should do that with humans too, by the way.
yeah, of course.
Yeah,
But you know, for me, because you talk about Italy and the notorious Mediterranean driving, because this is
yes.
where I grew up driving, and the interesting thing is it's like a switch for me. So I go there, I drive, no
Yes,
problem.
yes.
I come here, the switch, and I drive here, no problem. Totally different
Yeah.
personality. So
Yeah.
so humans are adapting also based on the driving environment.
Right.
Yeah. So
Excellent.
since this visit was you know, kind of replicate in-person visit, behind Shaurya is the atrium, which is between the engineering 1 and engineering 2 buildings.
Okay.
And then of course you would have come and met all the students and faculty. So I want to point to the faculty: Shaurya, Natalia, Naveen, Walter are here. Anybody else? Okay, so you would have met and chatted with all these faculty, and of course visited the labs, and the others are mostly students.
Yeah.
So
Perhaps
it's good for you.
perhaps it's
Yeah.
perhaps at some point this spring I should come over for a day visit.
Sure, yeah, that would be really nice, and meet the faculty in person. I think we are missing a couple of faculty. I thought Hatem was here, but he left. But anyway, I know you know Naveen, you know Natalia, Shaurya maybe the first time. Walter, actually Walter from UC Davis, also. So that's why we hired him when I was a chair, only because
Yes.
from UC Davis, and I
Now
felt disadvantaged.
I should tell you, Mohammed, I met with Susan Handy because we shared an office, and
Yeah.
I guess they tore down that old building where civil engineering was.
Oh,
Remember
really?